block dim. These are the predefined variables basically by the CUDA for thread indexing or block indexing. Block dim. These are the variables we will be using for creating the index block dim. It contains it is a predefined variable. It contains the dimensions of each thread block. Each thread block, that is dimensions mean it contains the number of threads in a block. Block dim means number of threads in the block, which is specified in the second configuration parameter for the kernel launch, right? Now another is the block IDX. This is the block index within the grid. Thread IDX, it is the thread index within a block. So these are block dim, block IDX, and thread IDX. These predefined variables are of type dim3, like block dim. So all these have three dimensions, that is dot x, dot y, and dot z. Block dim dot x, block dim dot y, and block dim dot z, and similarly for block IDX and thread IDX also. Now this statements, highlighted statement means these statements over here, this statement, it generates the global, that is a unique index for identification of a particular thread within a grid. It's a unique index for identification of a particular thread within a grid, basically. That is used to, this index is also used to access the elements of the arrays. So there is another predefined variable for grid identification, that is the grid dim. It contains basically the for the grid, it contains basically the grid dimension. It contains the dimensions of the grid, that is the number of blocks in the grid. Grid dim contains the number of blocks in the grid, which is specified as the first execution parameter to the kernel launch. So these arguments are passed by our host code to the kernel, and are these values are stored automatically by the CUDA runtime into these predefined variables. So this is just linear addressing. In this statement, we are multiplying the block index, x index. We are using only x index. Block idx dot x multiplied by number of threads in the block plus the thread index. So this is just a linear addressing, converting from a index of thread within a block to a index of thread in the grid. Right? I hope this statement is clear. We are creating a unique index I multiply by using this index of a block, that is block number. Block number may be 0, 1, 2, or up to, if we have launched the 256 blocks, then it will be up to 255. Block number multiplied by block dimensions, that is the number of threads in a block, that is 256 for here, plus thread index, right? So that is the linear addressing, linear index we have created, and same index we have used in over here. And this index should be less than the maximum index of the highest value of the array index, that is n, which we have passed as the first argument. Then yi is equal, that is the sexp computation, that y is equal to ax plus y. Now these are the things we have discussed. Now
Vikram,
yeah,
sorry, just a question. You can just go back to the previous slide, please.
yeah,
Where you showed, yeah. So now we've derived I as a block index dot x multiplied by block dimension dot x and things. So this is just an index only within the particular block, right?
which one? First one, block in IDX. No, this I tell you,
No, no, I would be
this index block IDX dot X. This is the index of the block. Which block? Block number, I mean to say. This is the block.
yes. So we gave a number of
Yeah,
correct. So we gave a configuration execution configuration called number of blocks. So that will determine number of block indices, right?
yeah, maybe 0 to whatever it is, 0 to, let's say, 0 to 255. If we have launched 256 blocks, right? And
We have
block
launched 256. Yeah. And each block has a dimension in X also, I think in our case as
256.
250, 256 with the number of threads is 256 in the block.
Yeah, 256. Yeah, it is 256 only. Yeah, you're right.
Uh,
And
and each block is 256 threads. So the thread ID x.x will also go from 0 to, is it 0 to 255 or is it 1 to 256?
0 to 255. It will also
Okay.
go from 0 to 255. Yeah, 0 to 250.
Okay. So yes. So what? So does this just compile to a code where each line of this just gets converted to one thread execution?
Yeah, yeah, that's right. It will be executed by each thread separately. This kernel will be executed by each thread processor separately. So, in this way, it will be uniquely able to access each our array elements.
And that's and if there are many elements,
Hmm. Yeah.
does it just uh, let's say the number of threads. Now in this case, I think if I do the arithmetic, we had 1 million elements in our array.
Yeah,
256. I
blocks.
think the number of blocks was 256.
Yeah,
No, no, blocks was not 256, right? I think blocks was n plus 255 divided by 256.
yeah, 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 yeah,
3,900 blocks or something.
yeah, yeah. Fine. Hmm. So total.
So, to, so now will it just try to distribute it across all the available resources on the GPU as is, or uh, we hope that it would do that? Is that what happens, or because there is only one grid now, right, in one kernel? My
See,
understanding is each kernel would run on a grid.
Means as I told you earlier that there is a maximum limit on number of blocks. For example, in this our GPU, let's say, supports maximum 1024 blocks, right? And in every blocks it supports, let's say, again 1024 threads. So it has capability to launch 1024 multiplied by 1024 threads in one grid.
Yes. So now this does this grid occupy all the resources of the
Oh yeah,
GPU?
it will occupy all the resources. Fine.
So when let's say then we have two kernels that are launched,
Yeah,
one each kernel will go on a different grid, right?
yeah, yeah, yeah,
So when both of them run in parallel, are all of them then contending for all the resources of the GPU?
yeah, yeah. See, in this, I think if there is a limit on the maximum number of threads, so total threads launched by all grids, they must be equal to the maximum specification of the GPU. Means we have to divide it among the resources among multiple kernels. We can't say that all the threads are being launched by one kernel, then it will be then they will not be able to execute properly, or it will give some error, or it will hang. Means we have to divide the resources between multiple grids.
Okay.
What I think.
Uh,
Yeah. Means there is maximum capability of uh, we we can't, we have to divide it among multiple kernels as per
so
the. Yeah, yeah, yeah.
Yeah, I have one more question. Let's say, for example, in the same code example, if you just roll back, let's say one more slide.
Yeah. One more.
Yeah, one more slide. I mean, where the
We can go back to the whole
whole
code.
code actually. Yeah.
I think one of the earlier slides which has the
Whole
full
code.
code.
Yeah.
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 Yes.
Yeah, let's say here, right in the code execution, where we call the kernel code with triple ankle vertex,
Yeah. Yeah.
correct, right?
Yeah.
Number of blocks in and threads per block is actually given as a parameter,
Yeah.
correct?
Yeah.
So does this indicate, let's say, for example, this number of blocks into a number of threads per block is actually less than the supported course number of cores, okay?
It should be less than or
So
equal
does this
to.
mean
Yeah.
less than or equal, right? So does this mean these many threads execute concurrently
Yeah. These execute concurrently.
at once?
That's. Yeah. Yeah.
Okay,
Sure. Sure.
that is first question. Second, let's say for example, I'll call one more instance, okay,
Okay.
of the same one more time, just as a one more launch, kernel launch, just
Okay.
after this.
Okay.
So,
I.
till the other threads, I'll have to wait till the threads execute because of the first kernel launch.
No, no, we can't wait. It depends upon you whether you want to wait or not wait. Basically,
No,
we
no,
have
no.
to
See,
wait
what
till
I'm
the time. We have to wait till the time our kernel complete its task. We cannot.
Correct. Correct. So
Yeah,
so Vikram, the question is now we called SAXPY. We made a call, right?
yeah.
Imagine that same line was copied again just below that. So we
I
have two
think
calls of SAX.
I think it will not be supported because we have
Yeah.
to
So
create the kernel with other name. I suppose some other
uh,
name. Same name may not
no,
be.
just
let's
call.
assume,
Just
yeah,
call the same
yeah.
kernel.
Okay.
We're just calling the kernel, right?
Yeah, yeah.
In SAXPI, num blocks, thread block, N2FDX we have a call, right?
Yeah, yeah.
Let's say we call that again just before we do CUDA mem CPI
Okay.
again.
Okay. Fine.
So which means the same kernel is launched twice, correct?
Okay.
So so now what would happen, because we've used a lot of the threads when the first one was called, and then we've come back to the code and we've issued one more, right?
Yeah, yeah.
So the question here was now will the second kernel really launch, because the first one would be running all of its threads by using all of the GPU.
Yeah, if we are calling multiple kernels, they will be launched in concurrently. Yeah, they will be launched concurrently. All they will be launched, will be executed in parallel, but we have to just divide the resources between these two. Means that there is a
Okay, so
maximum.
we
Yeah,
okay, so the total number of
threads
and the
launched.
resource here, because is it threads or is it blocks? Because blocks is the limit, right?
Yeah,
Do we
blocks.
have limits of threads?
We have the limit on threads in a particular block, and we have also the limit of number of blocks. Both.
Yes, those are the two limits, right?
Yeah, yeah,
Yes.
yeah. Those limits are there. Right.
Vikram, just a basic question to confirm. This operation A times xi plus yi, that is by itself one single thread, right?
Yeah, yeah. Yeah,
Okay.
it will be done by one single thread. For omega I is
Okay,
equal to zero.
I have a question. So if the n is very large, pretty large, larger than the total number of the threads in the GPU, what will happen?
Pardon? I didn't get the initial. Your question
If
initial.
the
Yeah.
number n is very large,
If the number n, capital N.
large, yeah,
Yeah.
yes, it's
Yeah.
larger than the total number of threads in the GPU, what
Okay.
will happen?
Okay. Now regarding this number n, we have to take care of 2 points. Fine. Because we have to allocate the memory onto the device. Our number n should not be so large because there is limit of global memory of our GPU, right? So we cannot.
Yeah, just say our GPU is not good. It's a old GPU. It doesn't have, for example, it only have 1 million threads in total. However, my vector is 2 millions. If we call this kernel, what will happen?
Well, if you are asking if the number of elements is too much, what will happen? Is it so?
Yeah, yeah.
But it will
Because as you mentioned, it looks like one thread for one
element.
operation, right? One
Yeah.
operation in the kernel. However, currently, if we don't have enough threads, we have too many elements. What will happen?
Yeah, that I'm telling you. No,
Simply crash
I've
or just
yeah. No, it will crash if our GPU does not support this much memory. First of the resource to be used is the memory, right? If the our GPU does not support this much memory, then it will crash. First thing. Secondly, if our GPU supports this much memory, then we have handled this part in our code. I just show you in our code. We have to go through this code once again. We have written a loop over here. We have written just sorry in our yeah. Okay, it is not loop over here. Fine, fine. Okay.
yeah. Over here in the code, it looks like you only use one grid.
Well, yeah, we have written one statement only.
You
No?
should have multiple grids, right? So here you only use one grid.
Yeah,
So
yeah.
the capital N is large enough. It may
Yeah, then
more than the
yeah.
threads in one grid, right?
Yeah. Then,
It's
then we
possible.
then we have to write the loops in our kernel. It means one thread will be processing the multiple elements, not only single element. Okay, that we will go into the subsequent programs. We will be writing the loop inside the kernel program, right? So, so over one kernel, over one thread will be executed not only on single element but multiple elements that we can do.
Because the number is less than that, you can run. What if the number
Okay, I
is
see. So it's more like the code need to be updated in the kernel side.
Yeah, we will have to update our kernel code to access all memory locations. That we can do.
take care and it will
Got it. Yeah.
That we will discuss in subsequent programs how we can do that. Right?
This much was given.
Hello, Vikram, can you hear me?
Yeah,
Hello.
yeah.
Yeah. What do we mean by __ global? Yeah.
Underscore global __ it is identifier for a kernel function. If we want to declare create a kernel, then we have to use this identifier.
What does it mean? Yeah.
Means that this code will be this is a parallel code, and this code will be executed on the device, not on the host. For to execute this kernel, we have to launch the multiple threads which we pass as arguments as configuration to this kernel. You can see here this is the kernel. We have invoked the kernel over here. We have passed these two arguments, right? Means this kernel function will be executed on the device, that is GPU, not in the serial fashion. That will be executed in the parallel fashion. That is the meaning of this __ global __, right?
Is there any other identifier than this global?
No. There is another identifier, __ device __. That is a function.
I think that's a keyword of the CUDA programming, right?
Pardon?
That's just keyword to the CUDA programming.
I didn't get you what you said. Please repeat.
Yeah, this is a global __.
Yeah.
The keywords of the CUDA programming only.
Yeah. This is the syntax for this creating the kernel function by the CUDA programming language. In the C language only, basically. In other languages, there may be other syntax, but in C, C++, this is the only syntax for this. Should we go ahead with?
Vikram,
Yeah.
one last. Okay, I have a question. Sorry. So this one runs on a default stream, right?
Yeah.
Because we haven't really provided that argument.
Yeah.
So when we do call the same kernel twice the same way, if it is still on the same stream, do they end up becoming parallel? Or
Yeah.
until we specify a different stream, do they become parallel?
No, they will end up being parallel even if they are launched on the same stream, because these kernels execute asynchronously basically. Means, for example, we have launched the kernel in the host code. We have written the kernel launch statement, and again in the next statement we are launching another kernel. The CPU will not stop at that kernel launch. It will go to the next statement. It will launch the second kernel and then will go. It is just like, okay, it has told the GPU to do this program, to execution of this kernel, and it will move on to its next statement in the code. So they keep on executing in parallel. Maybe there may be kernel 1, kernel 2, kernel 3, kernel 4. They will keep on executing in parallel on the device, and we can keep it on waiting by putting the statement CUDA thread synchronize if we want to wait for a kernel.
Yeah, one thing, we understand that it's non-blocking to the host side.
Yeah.
Host can continue.
Yeah.
But what happens on the GPU side? Whether the GPU is able to partition the cores properly for these two kernels and such that they run in parallel,
Yeah,
or
yeah.
on the GPU side, it's happening back to back.
It is happening in parallel and it is automatic. We do not control it. We cannot control it. It is
Then
yeah, it is handled by CUDA runtime by itself. But of course we can mention streams, etc. That we can do.